Okay, so as introduced by Corinna, the skeletal editing has now been recognized as new trend in the field of synthetic organic chemistry. And this is largely because of Mark's groundbreaking discovery of nitrogen deletion reaction and a series of single atom manipulation of cyclic motifs. And we are also working on transition metal catalyzed reactions that involve skeletal editing, although we did not describe them as skeletal editing at the time we started our program. And today, I'm going to talk about our skeletal editing reactions, which we termed UFC and SCAD. And if you search these words using Google, you will find that UFC is normally used for the Ultimate Fighting Championship, and that SCAD means spontaneous coronary artery dissection, a cause of a heart attack. However, these are not today's topics, and I will show you new meanings of UFC and SCAD. And our UFC stands for unimolecular fragment coupling, and UFC represents a reaction format where an atom or a small molecule, as described X in this scheme, is eliminated from the middle of the molecule, and the rest of the fragments are coupled to form a new bond. And for example, decarbonylation of carbonyl compounds or decarboxylation of esters are the typical examples of UFC. And in addition to CO and CO2, elimination of SO2 can also be used for catalytic UFC. And deletion of nitrogen from secondary amines, which was developed by Mark, is also an example of UFC. And UFC can serve as a potential alternative to cross-coupling because it uses readily available starting materials and does not require any other reagents except for catalysts, making it suitable for late-stage bond formation. However, the scope of UFC is currently much more limited than cross-coupling because the cleavage of strong chemical bonds is required for UFC to proceed. Therefore, to broaden the scope of UFC, we need a suitable catalyst that can activate strong chemical bonds such as CO and CC bonds. And in this context, we have been working for more than 10 years on transition metal catalyzed reaction that involve the activation of strong chemical bonds such as CO bonds in aerosols, CC bonds of nitriles, and many others, as you can see here. And by taking advantage of these bond activation catalysts, we have developed several UFC reactions, and I would like to talk about them in the first part of my presentation. And our contribution in this field started from the discovery of this decarbonylation reaction. The reaction of simple benzophenone derivative with the bond equivalent of nickel COD and an N-heterocyclic cyclic carbene ligand at 160 degrees was found to produce a decarbonylation product. And this reaction is quite interesting to us because these results demonstrate that nickel zero can activate a strong CC bond of simple unstrained ketones. The bi-aryl products are normally prepared by cross-coupling reactions using the corresponding aryl halides and aryl metal reagent. And our protocol demonstrates that UFC can be used as atom economical alternative to cross-coupling reactions. However, current limitation of our decarbonylation is that one equivalent of nickel is required, and we were unable to make this reaction catalytic in nickel. This is because the eliminated carbon monoxide strongly binds to nickel, which kills the catalytic activity. And we then turn our attention to decarbonylation of other carbonyl compounds. So for example, this type of amide derived from nitrogen heteroaromatics undergo decarbonylation with the catalytic amount of nickel, allowing for the formation of carbon-nitrogen bond by a UFC process. The eliminated CO can bind to nickel in this reaction as well, but this carbon-nitrogen bond is much weaker than a carbon-carbon bond of ketones, so the reaction can proceed in a catalytic manner. And interestingly, when this reaction was conducted in the presence of norbornene, we got this product. Okay, we got this product. Norbornene inserts into the carbon-carbon bond of amide. And this reaction is also an example of skeletal editing, in which the molecular skeleton is extended by cleaving the CC bond, followed by inserting a molecule there. And carbon-silicon bond formation is also possible by nickel-catalyzed decarbonylation of acylcyanates, as you can see here. As demonstrated in the previous slide, the catalytic decarbonylation of carbonyl compounds is potentially a powerful method for various bond formation using readily available starting materials. And catalytic decarboxylation, where CO2 is eliminated, is even more ideal reaction format of UFC, because the starting esters can be readily prepared from the corresponding carboxylic acid and alcohols. Now, overall, we can make a variety of chemical bonds simply by eliminating H2O and CO2. However, to date, the scope of this catalytic decarboxylation is highly limited. The catalytic decarboxylation is known to occur when allylic esters shown here are used as substrates. And this reaction is initiated by the cleavage of an allylic carbon-oxygen bond, which is facilitated by the formation of a stable pi-allyl-palladium intermediate shown here. And also, this 1,3-dicarbonyl moiety is required for the subsequent decarboxylation to take place. Therefore, the scope of the esters in this reaction is limited to allylic esters bearing 1,3-dicarbonyl fragments. And to develop more general decarboxylation methods, we need a catalyst that can cleave non-allylic CO bonds. And in this context, our group has been studying on nickel-catalyzed activation of CO bonds in phenol derivatives. And this experience led us to investigate the decarboxylation of these phenol esters using the nickel catalyst, since nickel can mediate the oxidative addition of the CO bond here to form this intermediate, which will then undergo decarboxylation, allowing for the catalytic decarboxylation of non-allylic substrates. And our hypothesis was in fact realized when the substituent here is an amino group. So this is the reaction that we have developed. And simply heating this aromatic carbamate in the presence of a nickel catalyst at 160 degrees led to the formation of the aniline derivatives by decarboxylation. And the key here is the use of this polymer-supported phosphine ligand, which was originally developed by Sawamura and Iwai at Hokkaido University in Japan. And this ligand system efficiently promotes the difficult CO bond activation process. And the aniline derivatives are normally synthesized by Buckball-Hartwig type amination reaction. But our amination method is very unique because free amines are not required. So we can make carbon-nitrogen bond without using free amines. Because of this unique feature, our amination can proceed even in the presence of an aldehyde moiety, as you can see here. An aldehyde does not tolerate Buckball-Hartwig conditions. And fluorine derivatives or less nucleophilic diphenyl amino derivative can also be used for this amination reaction via the decarboxylation. And when we think about UFC of esters, decarboxylation is not the only option. Decarbonylation of esters to give ethers is another mode of UFC of esters. However, decarbonylation of esters is much less explored, and only 2 examples using the nickel catalyst was reported to date. And the third type of UFC of esters is deoxygenation, which would give ketones. And this mode of reaction can be viewed as a Ritro-Bayer-Villiger reaction and has not been accomplished to date. And quite recently, we have developed the first example of catalytic deoxygenation of esters, as you can see in this slide. The allylic esters can be deoxygenated under photoirradiation by the dual use of a nickel catalyst and a photoredox catalyst in the presence of 1 equivalent of triphenylhosphine. And triphenylhosphine serves as a stoichiometric reductant to accept an oxygen atom from the ester. And a possible mechanism is shown here. The nickel catalyst promotes the oxidative addition of allylic esters to form the pi-allyl nickel species shown here, and carboxylate anion is dissociated. On the other hand, triphenylhosphine is oxidized by the action of a photo or redox catalyst to generate a hosphine radical cation, which then react with the carboxylate anion to form this tetracoordinate phosphoramide radical, as shown here. And this phosphoramide radical is known to undergo beta scission to generate the acyl radical with the revelation of hosphine oxide. The resulting acyl radical then react with pi-L nickel species to form the deoxygenation product by reductive elimination. And this work was initiated by the research proposal by Ryoma and Riku, and I am very happy that they were actually able to bring this project to publication. So during the investigation of UFC as new tools for organic synthesis, we noticed that amides are one of the most ideal starting materials, since amides are everywhere in pharmaceuticals and organic materials, and they can be readily prepared from carboxylic acids and amines. However, the elimination of isocyanate from amides have not been reported at the time we initiated our study. And this project was led by Ryoma. And after completing this UFC project, Ryoma spent several months in Mark's lab as an exchange student and involved in skeletal editing research, also in the US. So based on the great success on the palladium catalyzed decarboxylation of allylic esters, we initially investigated the reaction using this urea derivative with an allyl group and an imidazole in the presence of a palladium catalyst, and found that the elimination of isocyanate indeed occurred to form this allylic imidazole. And the reaction possibly proceeds through the formation of this pi-allyl palladium species, followed by carbon-nitrogen bond cleavage to eliminate isocyanate. And by using this protocol, not only the nitrogen heterocycles, but also the aliphatic amines or aniline derivatives, and even thiol can be used successfully in this catalytic UFC reaction. And UFC of amides can also be applied to the carbon-carbon bond formation reactions by using amides derived from beta keto acids, as you can see here. The reaction proceeds in group yields with bulky groups such as benzyl at the alpha position of the ketone, successfully generating a sterically congested all-carbon quaternary stereocenters. And 6-member ring can also be used successfully. And in addition to allylic amides, naphthyl methyl group, as shown here, can also be activated and participate in this UFC reaction. Okay, so in this slide, I would like to talk about the synthetic application of this UFC of amides. Amide group having an aminoquinoline moiety is known to serve as a directing group for CH bond activation reaction. So for example, this amide having an aminoquinoline can be elevated by a palladium catalyst in which the CH bond of this methyl group is directly substituted by this blue arrow group, as you can see here. And then this NH group is elevated, resulting in the formation of this amide. And this can undergo our UFC reaction in the presence of a palladium catalyst to give this elevated product. So as a result, the aminoquinoline moiety can serve as a removable directing group in the CH bond functionalization reaction. And late stage conversion of the directing group will broaden the synthetic utility of the directed CH bond functionalization reactions. And we next investigated the fate of the eliminated isocyanate by fluorine NMR. And when this urea was reacted under the standard reaction conditions, the elevated imidazole was produced in 90% yield. And at the same time, isocyanate and its cyclic trimer, shown here, were produced in 10 and 83% yield, respectively. So we next think about intercepting the eliminated isocyanate with a tetrad nucleophile in the substrate. So when a substrate bearing a primary alcohol moiety, shown here, was used, the eliminated isocyanate is trapped by this hydroxy group, resulting in the formation of this product in 92% isolated yield. And this is a unique representation of skeletal editing in which a part of the molecule was cut from one place and was pasted onto another place. And this cut and paste type UFC can be applied to a series of substrates. So a longer alkyl chain is also applicable, as you can see here. And in this example, the amide group migrated from here to there through 12 atoms. And not only primary alcohol, but also amino group are effectively capture the eliminated isocyanate. And furthermore, the migratory UFC is applicable to the urea substrate, as you can see in this example. And here, the secondary alcohol can intercept the eliminated isocyanate to form this product. Okay, so let me discuss the energy balance of this process based on DFT calculations. So in the simple UFC of amides, the elimination of isocyanate is a slightly endo-ergonic process. However, the subsequent trimerization of an isocyanate is the trimerization to form a cyclic trimer made the overall process exoergonic, as you can see here. So this can give the thermodynamic driving force for the overall UFC process. And in contrast, in the cut-and-paste type migratory UFC, the isocyanate was captured by the tetrad nucleophile before trimerization. However, even higher energy gain was obtained by the capture of isocyanate with the tetrad hydroxy group. So this indicates that the migratory UFC pathway was highly favored over the simple UFC. So, okay, I have talked so far about UFC. So let me move on to the second topic, the SCAD reaction. And in my presentation, the SCAD stands for the single carbon atom doping. And non-charged electronically unsaturated carbon species play a key role in synthetic organic chemistry, especially as reactive intermediates. And among them, radicals and carbenes, especially common species, because reliable protocols were established to generate and control these reactive species. And monovalent carbene is also known, although the synthetic application of this species is much limited compared with radicals and carbenes. And one of the advantages of using these electronically unsaturated carbon species is the number of chemical bonds that can be formed at the carbon center. As the number of electrons decreases, the number of formable bonds increases. In the case of carbene, we can make 3 new chemical bonds at the single carbon center in principle. So in this context, the atomic carbon is an attractive reactive intermediate because we can make 4 different bonds at the carbon center in a single step. However, the use of atomic carbon in synthetic organic chemistry is quite challenging because its lifetime is too short to be used in synthesis, and no suitable precursors are developed. And if we can insert an atomic carbon into an organic molecule, we would edit the molecular skeleton dramatically by forming 4 new chemical bonds. And we termed such a reaction as a SCAD reaction. SCAD reactions were indeed reported to occur using an atomic carbon that is generated by a physical method, such as arc discharge. So for example, the T-butylbenzene is converted to this alkene or 5-membered ring compound, although the yield is less than 1%. However, these examples demonstrate the potential utility of SCAD reactions, since the classical synthetic chemistry cannot achieve this type of unusual transformation. And several compounds that can serve as an atomic carbon precursor were also reported. So for example, this compound is called carbon suboxide and is known to generate an atomic carbon by photoirradiation via elimination of carbon monoxide. And thus generated atomic carbon is used for the insertion into ethylene to form alene. And this diazotitrazole was also reported to be used as an atomic carbon precursor, which reacts with furane to form an unusual SCAD product, as you can see here. And although these examples also demonstrate the synthetic potential of SCAD reactions, it is still difficult to control the high reactivity of an atomic carbon generated from these precursors. And in our study, we found that the N-heterocyclic carbene can serve as an atomic carbon equivalent and can be used for a new SCAD reaction, as shown here. Acyclic amides are transformed into the gamma lactams by incorporating a single carbon atom. And 4 new single bonds are formed at 1 carbon center. And I would like to talk about this reaction in more detail. So in the past, we are investigating this NHC catalyzed reaction of this unsaturated amides. And in this reaction, the phenyl group on the nitrogen atom is in the study material migrates to the beta carbon. So this process involves catalytic nucleophilic aromatic substitution reaction. So this reaction can be explained by assuming that this E-like intermediate is initially generated by the reaction with NHC, and the carbon ion here in the E-like intermediate then attacks the ipso carbon of the aniline moiety. And this reaction is a unique example of the organocatalytic cleavage of a carbon-nitrogen bond of aniline derivatives. And in this CN bond cleavage reaction, the most effective catalyst was an NSC bearing a bulky 2,6-dimethyl substituted aryl groups. And during the course of the catalyst screening in this reaction, Miharu was careful enough to notice that a small amount of a gamma-lactam product was formed when less bulky NAC with no auto-substituting was used as a catalyst. And the comparison of the molecular formula of the starting material and this gamma-lactam product led us to confirm that only a single carbon atom is incorporated into the product during this process. Thus, the SCAD reaction took place here. And to optimize the yield of the gamma-lactam, we next examined several NACs using one equivalent of them. And as you can see, the alkyl substituted NAC were found to work better. And finally, we identified that the cyclohexyl substituted NAC gave the SCAD product with highest yield of 91% yield. And the origin of the incorporated carbon atom was unambiguously confirmed by conducting the reaction using the carbon-13 labeled NSC shown here. And as a result, the carbon-13 was indeed incorporated into the gamma-lactam product, providing the experimental evidence that the C2 carbon of the NSC can serve as an atomic carbon equivalent. So here is the scope of this SCAD reaction. The halide, methoxy group, and ortho substituents are all compatible with this reaction to provide the corresponding gamma-lactams. And bulky isopropyl group or pi-extended naphthalene can also be used in this SCAD reaction. And this method can also be used for the modification of biologically active compounds. For example, the aniline moiety of this compound is known as a certain enzyme inhibitor. And after introducing an acyl group here, this can be transformed into the corresponding gamma-lactam derivative without touching the imido moiety, which is potentially reactive to our nucleophile. Now, let me explain the possible mechanism for this reaction. So NSC attacks the unsaturated amide to form the ylide intermediate shown here. And this carbon ion in the ylide then attacks the ipso or carbon of the aryl group to undergo nucleophilic aromatic substitution to liberate this nitrogen anion shown here. And the mechanism so far is completely the same as that I showed in the CN bond cleavage reaction. And in that reaction, this amide anion obstructs the proton alpha to the carbonyl moiety to liberate the NAC catalyst and the unsaturated amide when the bulky NAC was used as a catalyst. But in the SCAD reaction, we need to use less bulky NAC, which allows this nitrogen anion to attack the C2 position of this imidazole moiety to generate this spiral intermediate. And this spiral intermediate has the ortho-amide substructure, and it is easy to cleave one of the carbon-nitrogen bonds to generate this iminium ion. And this iminium ion then isomerizes to enamine, and further isomerization occurs to form this more stable conjugated amide. And the carbon-nitrogen bond of the amino moiety is then cleaved, probably because the electron pushing from this nitrogen can liberate a stable hydroxypyrrole anion shown here. And finally, protonation of this hydroxypyrrole anion give gamma-lactam product along with 1,2-diimine. And although this mechanism seems a bit complicated at first glance, this involves only classical polar reaction mechanism. And we have several experimental supports for this proposed mechanism. So regarding the formation of this ylide intermediate, when we stopped the reaction in a shorter reaction time, namely 2 hours, we were able to isolate the ylide intermediate in its protonated form, as you can see here. And we also confirmed that this protonated ylide intermediate can be converted into the gamma lactam by heating in the presence of a base. So these results support the intermediacy of the postulated elide intermediate. And regarding the intermediacy of this spiral intermediate, we noticed a paper that claims that the reaction of this acrylamide with triazole-based NAC generate this spiral lactam. And this spiral compound is possibly generated by the addition of NAC to form the enolate, and followed by deprotonation of the lactam product. And this was found to be true. And although we were unable to isolate this spiral intermediate, the final lactam was actually formed. And we believe that these results support the intermediacy of this spiral intermediate. And we found that this experiment is not just a mechanistic study. So this indicates that we can broaden the scope of the SCAD reaction. So at the beginning, we needed to use the N-elevated amide as substrates, and the substitution at the alkene terminal was not tolerated. But now we can use even more simpler NH amide as substrates for SCAD reaction. So here is the scope of the SCAD reaction using NH amides, and a series of 1,2 disubstituted acrylamides successfully participate in this SCAD reaction to form the corresponding gamma lactams. And cyclopropyl group, cyclic amines, and some bicyclic systems all underwent the single carbon atom doping reaction. Okay, so let me summarize my talk today. I have introduced two reaction formats, UFC and SCAD, which are potentially useful as tools for skeletal editing. And we are currently working hard to further broaden the scope of these reactions. And finally, I would like to thank all of my coworkers for the ideas and the experimental works to realize UFC, SCAD, and many other new reactions. And thank you for your kind attention.
Thank you. Excuse me. Sorry. Thank you very much for your talk, Professor Mamoru Tobisu. This was very exciting. So with this, I'm opening the Q&A session.
Okay.
And with this, I'll start the first question from the audience. And this actually relates to the mechanism. It says the mechanism needs this high temperature. Does the NAD addition or, sorry, let me just read this again.
So the question is about the last reaction, SCAD reaction.
I do read it like this. The mechanism needs this high temperature, the NHC addition or elide insertion step. Does the tetrahedron letters paper from 2015 just need room temperature to achieve the product?
Okay, so I think the higher temperature is required for the final step, the elimination of 1,2-diimine moiety from the spiral intermediate. Because even at room temperature, we can observe the formation of the elide intermediate. So probably the rate limiting step of the overall process is the later step in this sequence.
Yeah, I think that clarifies it. I think the colleague from the audience just clarified this and says, thanks for the impressive talk. And then in the NHC chemistry, very high temperature was used. So I wonder which step in the mechanism needs this high temperature, the NHC addition or the elide insertion step.
the collapse of the spiral intermediate requires a high temperature, I think.
Okay.
Okay.
Thanks for clarifying that. We're waiting for the next question, I think. So I see the next question in the chat right now. In UFC, did you also observe the rearrangement of the isocyanate intermediate to the corresponding carbamide or amide intermediate?
So I couldn't understand the meaning of the question. So in the UFC reaction?
Yeah. Did you also observe the rearrangement of the isocyanate intermediate to the corresponding amide?
Amide?
Yeah, or the corresponding. The CO and H2 corresponding product.
CONH2. So I don't understand. So the isocyanate can isomerize to the amide. Sorry, I don't understand the meaning of the reaction. So the question.
Could the colleague please clarify that question? So I'm moving on to the next question in this case. In a SCAD reaction, or is the SCAD reaction applicable for other heterocyclic analog synthesis?
Other, okay, yes. So actually, we have examined a variety of the electrophiles that can be attacked by an NSC, but so far we were successful only when we used the alpha-beta unsaturated amide derivatives. And we are currently working hard to further expand the scope of the reaction to for the synthesis of other heterocycles. But so far, they are unsuccessful.
Okay, the next question is, amides are very ubiquitous functional groups. Are there any examples of amide bond deletion that have so far been tried out in peptides and nucleobases?
So unfortunately, at this stage, our deletion of amide moiety can only be applied to the allylic amides. So we need to further expand the scope of the substrate if we would like to apply these methods to the peptide or more complicated starting materials.
Good. And on page 9 of your talk, what is the advantage of using the polystyrene-based ligand?
Okay, yeah, that's a good question. So this one. So in general, in the nickel catalyzed reaction, when we mix the nickel precursor with this phosphine ligand in the solution phase, we can get the mixture of 1-to-1 metal-to ligand complexation and 1-to-2 metal-to ligand complexation. And 1-to-2 complexation is no good for the catalytic activity because the coordinatively saturated species are less active. But by immobilizing the phosphine ligand onto the polymer support, we can avoid the formation of the 1-to-2 metal-to ligand complexation. And also, in the solution phase, the formation of the nickel-1 species by the comproportionation reaction, the reaction of the nickel-0 and nickel-2 species leads to the formation of the nickel-1 species. And nickel-1 is also a catalytically inactive species. And such a comproportionation reaction can also be avoided by immobilizing the ligand onto the polymer support, because the reaction between two nickel species can be avoided by immobilizing the ligand onto the polymer support. That's the two major reasons.
Thank you. So the next question, we have a very active audience. This is phenomenal. The next question would be, could you think of a catalytic version of the SCAD reaction using aldehydes as carbon equivalents?
Aldehyde as the carbon equivalent. That's a very, ideal reaction. Yeah, but yes. Of course, I would like to make this reaction catalytic, but so far, we were unable to do that. So I hope everybody can participate in this area, and yeah, in someday the catalytic version will be realized.
Okay.
Thank you for the comment.
And then we have a clarification from the colleague who asked the earlier question. So in UFC, did you also observe the rearrangement of the isocyanate intermediate? So the clarification is now that the colleague means the migration of the aryl group from the carbon to the nitrogen.
Sorry, I don't understand the question. In the migration of amide?
The emigration, sorry, in the UFC, reaction, did you observe the rearrangement of the isocyanate intermediate to that amide? So in other words, the colleague means the migration of the aryl group from the carbon or to carbon from the nitrogen. Migration of aryl to carbon from the nitrogen.
So basically, in the reaction that I showed today, no byproducts were observed. So such a carbon to nitrogen migration did not occur under these conditions. Okay.
Yeah, I think that clarifies it. The next question would be, Stas, the great work. Could you elaborate a little bit on the oxidative addition of the decarboxylative UFC reaction? Basically, nickel is just abstracting the aryl group, but not inserting into the bond.
Oxidative addition of, sorry?
Could you elaborate on the oxidative addition step of the decarboxylative UFC reaction? And I think the question is it true?
Decarboxylative.
Yeah. Is it true that nickel is subtracting the aryl group or facilitating the abstraction of the aryl group, but it's not directly inserting into the bond?
So the oxidative addition of, for example, aryl carbamate shown here is a well-known reaction. And this type of oxidative addition complex can be isolated. So because of that, I believe that the oxidative addition, the insertion of nickel into this carbon-oxygen bond is involved in this reaction as well.
Okay, I think that also clarifies it. And one final question, among many that we have, is this one: are there reactions that are applicable to triazine frameworks?
Triazine? Triazine? So could you say it again, please?
Are there reactions, or are the reactions in general applicable to triazine frameworks?
Other reaction?
No, the reactions that you presented, sorry, applicable to triazine frameworks. So could you potentially conduct these types of transformations on triazines? That's how I understand the question.
Triazine?
Yeah.
So I don't understand that. What is triazine?
I think this is the corresponding heterocyclic adduct, right? That you would potentially get as a product. Could you basically tolerate those types of systems or scaffolds under the reaction conditions?
So I am not sure. So I know the 1,2,3 triazole.
Yeah.
That also sometimes decomposes and in the presence of the nickel zero catalyst, but I'm not sure about the reactivity of the triazine. So I'm sorry, I can't answer the question.
Yeah, that's great. For this, Professor Tobisu, thank you so much again for joining us today. I know that it's very late in the evening for you, so thank you very much for devoting and donating your evening for this today. It's been a true pleasure to have you here with us. And I really thank you again for joining and also for contributing to our special issue and for your continuous support.
Thank you very much.